Okay, there we go. So we are on page 16. Once again, if you don't catch anything as we go along, don't worry, because we're going to go through it afterwards. So you can choose to write as we go, or you can choose to not. Ms. K, I had to borrow your book because Kinsley does not have a book and there's no extra back there. So I will not my book. I don't have yeah. Anyway. Okay. Here we go. Yep.
In this video, we're going to look at how scientists discovered that atoms have a nucleus in them. This discovery was...
Okay, so this is how they discovered the nucleus. We need to make this big. And we want to have our subtitles on. There we go.
Made by Ernest Rutherford, as well as his colleagues, in 1911. And they made this discovery with their famous gold foil experiment. And we're going to talk about that here. So atoms. This is sort of how we think about atoms today, with electrons on the outside, and then in the middle, a dense, hard nucleus that's where the protons and neutrons live. But it wasn't always like this. Before Ernest Rutherford and his co-workers did their experiment, this is what scientists thought the atom looked like. They called it the plum pudding atom. Now, plum pudding is kind of a British thing. So if you're American, it might be better to call this the blueberry muffin model. Think about this. You take a blueberry muffin and break it in half. What do you see on the inside of that muffin? Well, you'll see blueberries, and the blueberries are just kind of randomly stuck into dough. And that is exactly what scientists thought the atom looked like at a very small scale.
So just so you know, when we go and there's about 2 people who won't want to rewrite the quiz from yesterday. I'm not going to give them back to you today because I need to go through them myself and, check things over and whatever. But in general, it looked like most people didn't study. So we're all going to redo it other than the 2 people who got perfect on it, okay? But one of the things you're going to need to do on that quiz is you're going to need to label the diagram. So for example, what that's going to look like is for the plum pudding model, you're going to be labeling the electron and the positively charged dough or pudding, okay? And you should know that that is Thomson. And what did we call that model? Plum pudding. What was the model before that? Dalton and the billiard ball. And that one's really easy. It's just an indivisible sphere. So if you just draw a circle for that one, that's super easy. And today we're going to get to the 3rd model. Don't worry, the rewrite of the quiz is going to come after we've done all the models. So you'll be like really ready for it this time, okay?
Are just kind of randomly stuck into dough. And that is exactly what scientists thought the atom looked like at a very small scale. That electrons were sort of like blueberries, and they were stuck in this dough, kind of, that was positively charged. So you got this positively charged dough with electrons stuck randomly in it. This is the plum pudding model, but of course it turned out not to be true. Here's how Rutherford and his co-workers showed that the atom had a nucleus and that the plum pudding model wasn't right. They started out with a piece of gold foil, which is like tin foil or aluminum foil, except it's made of gold. I mean, wouldn't this be awesome to like wrap your sandwiches in for lunch? Anyway, I don't know, maybe if you're really rich, you use gold foil to like prepare your lunch. Anyway, they took this piece of gold foil and they shot tiny little things at it. What they shot at it were called alpha particles, which are tiny positively charged particles that are much, much, much smaller than an atom. So they take the gold foil, they bam, 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 shoot alpha particles at it. Now they want to know what happens to the alpha particles after they hit the gold foil. So here's what they do. They take a material that flashes when it gets hit by alpha particles, and they take this material and they bend it around into a circle like this. So wherever the alpha particles hit, they'll see a flash. They take this material and then they take their piece of gold foil and they put it right here in the middle of the circle. So now they shoot alpha particles into the gold foil and they'll see a flash somewhere on this circle that will tell them where the alpha particle ended up after it hit the gold foil. Now here's what they see. Most of the time, they shoot alpha particles, bam, 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 here at the gold foil, straight on, and they see flashes right here, behind the gold foil. So,
does that make sense? They're shooting the alpha particles this way, and they see flashes here, where the alpha particles hit the screen. Does that make sense? Okay.
This would indicate that the alpha particles are going right through the atoms of the gold foil and are ending up over here. So that's the first thing they notice. The second thing is a really huge surprise. When they shoot the alpha particles every once in a while, they don't see a flash here. Instead, they see a flash over here, or a flash over here, or sometimes a flash here or here, which makes them think that the alpha particles are hitting the gold foil and are veering off to the side once in a while. Or sometimes they're hitting the gold foil and they're bouncing back completely, all the way back. So, we can kind of summarize what they see using a diagram like this. Here we've got our circular detector screen that flashes. Here's an alpha particle emitter, which is just a fancy word for an alpha particle gun, something that's shooting alpha particles. Most of the time these alpha particles hit the gold foil and they go right through, and we see flashes on the screen on the other side. But every once in a while, an alpha particle will hit the gold foil, zoom, zoom, and will veer off to the side and flash over here. And every once in a while, it will hit the gold foil and will bounce back almost 180 degrees. Flash here and flash here. So, based on these two pieces of information, Rutherford and his team are able to make some conclusions about what the atom actually looks like. Here's the conclusions that they come to. Let's start with this gold foil, okay? The gold foil that they use is incredibly, incredibly thin. And in fact, it's so thin that these guys reason that there are only a few atoms in its thickness, that it's only a few atoms thick. So let's look at it on its side here and look at a magnified view of the gold foil. If we want to think about gold atoms as being sort of circles or balls, this is what the view from the side of the gold foil might look like. Just 2 atoms thick here. Now, let's think about the results that they got from the gold foil experiment, okay? The first thing that they saw is that most of the time, the alpha particles seem to have gone straight through the gold foil. So, based on this information, they're able to reason that most of the atom is empty space. Or if there's something there, it's very light. It's not very dense, and it's really easy for the alpha particles to shoot right through. So most of the atom is probably empty space. But now the second thing they see is that every once in a while, an alpha particle, zoom, veers off to the side, or it's like it hits the gold foil and bounces back. And so based on this information, they reason that while most of the atom is probably empty space, they think that there must be something very small, but very hard inside each atom. And here's a drawing here. Of course, you know that this is the nucleus now, but they didn't know that the nucleus existed, so they had to discover it here. And so they think there must be something really, really hard. And when an alpha particle hits it head on, bam, that alpha particle's gonna ricochet back. And they also notice, as we said, that sometimes the alpha particle veers to the side. They say, well, maybe it's because it hits the nucleus on the side of it, so it goes off like that. Or they also said maybe since alpha particles are positively charged, maybe the nucleus is positively charged, so that if the alpha particle comes close to it, remember, things that have the same charge repel each other. So you've got this alpha particle coming close to a positively charged nucleus, then zoom, it's going to veer off to the side because they're pushing away from each other. So regardless, based on this information, they reason that there is something small and hard in the atoms that once in a while the alpha particles are banging into, and that's what's causing them to bounce back or to veer off course. And they also reason that whatever this nucleus is made of, it's probably positively charged because of the way it looks like the alpha particles are sometimes getting repelled and pushed away. So if you take these two pieces of information together, we can come up with a model for the atom that looks like this, where this is just a combination of those two things that I saw, where we've got these gold atoms lined up, and most of the time, if alpha particles pass through so they don't hit any nucleus here, they just go straight on through. But if an alpha particle hits this hard, dense nucleus, or is close enough to be repelled by its charge, it veers off or it bounces back. So here's how the gold foil experiment changes how scientists think about the atom. Okay, so as we said before, here's a plum pudding atom with these electrons stuck in a positively charged kind of pudding. But Rutherford's experiment shows that this isn't quite true. Instead, he comes up with a model like this, where there is a hard, dense nucleus in the middle, and that is where the positive charge is. So the positive charge isn't like this kind of blueberry muffin dough that's spread throughout the atom, but instead the positive charge, everything that I've drawn in red here, the positive charge is concentrated right here in the middle of the atom, and then there might be some electrons floating around on the outside, but they're certainly not held in place because of the positively charged dough. Now, this is just one piece in a puzzle of figuring out what the atom actually looks like. So shortly thereafter, Rutherford comes up with this model for the atom, but then scientists realize that the electrons probably aren't just stuck in place, and instead they think that the electrons are spinning around the outside of the atom, and you still have this hard, dense nucleus in the middle. And then only a short while after this, it's discovered that the nucleus isn't just a hard piece of positive charge, but that the nucleus is actually made of protons, each one of which has a positive charge, and then the electrons are spinning around the outside. Now this is what we call the nuclear atom, because it has a nucleus. So we've got the nucleus of protons, and then electrons spinning around the outside. But of course, you probably know this still isn't an accurate representation of exactly what the atom looks like. In fact, they're totally missing the neutrons. It wasn't until the 1930s that James Chadwick and his colleagues discovered that there are neutrons, neutrally charged subatomic particles, in the nucleus of an atom. And then, as I've alluded to before, it's not that the electrons are really spinning around in circular orbits, but it's more like they're just buzzing around like crazy hyperactive flies all over the atom. But we'll get to all that later. For right now, all you need to know is that Ernest Rutherford's gold foil experiment showed that the atom was mostly empty space, but that it had something hard, something dense, and something positively charged that the alpha particles sometimes hit and bounced back. Now I want to talk about one more thing that can be confusing but it's really important. And it has to do with the predictions that Rutherford made, what he was expecting to see. Okay, now when people first learn about the gold foil experiment, they're often really shocked that the alpha particles went straight through the gold foil. And they think that Rutherford and his co-workers must have been really shocked as well when they found this out. But it turns out,
imagine Rutherford and his colleagues. They're sitting there thinking, I have a blueberry muffin, and I'm going to fire these alpha particles at it. It's just like shooting a gun at a blueberry muffin. What would you expect to happen to the bullet if it went and hit a blueberry muffin? Would it bounce back? No, it would just go straight through. So that's why Rutherford and his colleagues thought that these alpha particles should just go straight through, because that dough is just very light and fluffy and wouldn't provide a barrier to the bullets or the alpha particles at all. Okay?
that Rutherford was actually expecting the alpha particles to go through the gold foil. He thought that if atoms were the plum pudding model, that the alpha particles would have gone straight through. Because he thought that this positively charged dough was so light that the alpha particles would just be able to pierce right through it like bullets through a giant blueberry muffin. And sure, there are some electrons there, but compared to an alpha particle, an electron is so tiny, it's like a poppy seed compared to a bullet. And so he thought that that bullet would just fly right through the plum pudding atoms. Now, if you want to think of a model of the atom that would have made the alpha particles bounce away, it would have been...
Whose model would that be? Where we've got these alpha particles that come along and they hit this hard sphere and they bounce right back. Lucas? That's our billiard ball model. What scientist is associated with that? That is Dalton, okay? So that's what would have happened if Dalton's model was right. This is what would have happened if the plum pudding model was right. And then, of course, we saw something
in Dalton's model, which was one of the first models of the atom. Dalton thought that atoms were hard, indestructible balls. And so if atoms had really been like Dalton thought, sure, the alpha particles would have hit them and would have bounced away. But if the atoms were the plum pudding model, because this positively charged dough is so light, Rutherford thought that the alpha particles would go straight through. So when it turned out that the alpha particles went straight through the gold foil, it wasn't really that much of a shock. But what was a shock was when sometimes the alpha particles would veer off to the side or would bounce back. This is what was really shocking. And it told Rutherford that instead of the positive charge being distributed throughout in this kind of dough, that the positive charge was concentrated here in the nucleus. So that's what led them to the model of the nuclear atom with a nucleus. So it might even be better to draw the nuclear atom like this, where instead of having this pink positively charged dough, there really isn't anything here at all. And it's just all of this positive charge is focused right here in the middle of the atom. Now, it's almost not even good to draw these atoms as if they're shells with a nucleus in the middle, because it's not like they have shells. A more accurate way to talk about this is to say that the shells, what I'm drawing as the shells, are really just the outer limits of where the electrons go. Okay? And so what's between what I'm drawing as a shell and the nucleus is really just where the electrons live. But they're tiny and they're moving around all the time, so there's really not much there. So in fact...
So this little circle here, the black circle, that just represents the outer edge of the atom. It's not really representing anything specific. What's in there? Mostly empty space, with electrons just kind of living in there. And Rutherford had no idea what those electrons were doing. He's just like, we got all this empty space, and somewhere in there, there's electrons. And in the very middle, there's a nucleus.
Maybe one of the best ways to draw the nuclear atom would to be like this, where there isn't a shell, but there's a nucleus in the middle of each atom, and then you can kind of see a circle here, which is the outer reaches of where the electrons go. But then, of course, this isn't a perfect view of electrons, because instead of going around in circles, they sort of buzz around in various shapes. But
I actually don't love this version of the nuclear model. I kind of prefer the one where you've just got that boundary and you're like, in there somewhere there's electrons. But if you want to draw it like this, that's perfectly fine too.
again, that's getting a little ahead of ourselves. What the main important points are here is that Rutherford's gold foil experiment disproved the plum pudding model of the atom. It wasn't that there was positive charge all throughout the atom, like the dough in a blueberry muffin, but that it was the positive charge was heavily concentrated in a very hard, very dense nucleus in the middle of the atom, and then the electrons were on the outside of it. So that is how Ernest Rutherford, Hans Geiger, and Ernest Marsden discovered the nucleus with their gold foil experiment.
Okay. And we're not going to look at...
Let's talk about how Robert Millikan and
No, we're not going to. So let's go through this and fill in everything. Hans Geiger, Ernest Marsden, you're not responsible for those names. And Ernest Rutherford. Do you needed to know his first name? No, just his last name, but we're going to write down the whole thing anyway. Ernest Rutherford. And they came up with this idea of what kind of particles? Alpha particles. The symbol for alpha almost looks like a little fish. Okay, that's the symbol for alpha. They are tiny and they have a positive charge, so they are positively charged particles. They are much smaller than atoms. So here we have an alpha particle emitter. So we can just write alpha emitter. I'm going to grab myself an answer because I don't know if it's not big box under it. Oh, it just says on particle of Now, where do the alpha particles go? They go this way. They go this way. Most of them go that way, but a few go back. And what's that yellow thing in the middle? That's our gold foil. And you don't need to know this, but this circle around the outside, I'm going to label it, but you don't need to know this word. This is a phosphorescent screen. And it flashes when hit by an alpha particle. So that's your choice whether you want to write that down or not, okay? The particles Rutherford fired at the gold foil were called alpha particles. Are these particles big or small? Small. And they are positive or negative? Positive. The gold foil that they used was very thin. How many atoms thick was it? Only a few. Now, these are the first three letters of the Greek alphabet: alpha, beta, and gamma. What type of particles did we use? Alpha particles. Did they bounce off? Did most of them bounce off or go straight through the gold foil? Most went straight through. Therefore, if they went straight through, most of the atom must be empty space. But every once in a while, which of these ones? Alpha, the little fishy looking one. The alpha particle will veer to the side or even bounce back. As long as you get the general idea, it's not, the actual words are not super important. Do you know what I mean? So even though most of the atom is empty space, most of those particles are going straight through. Empty space. There must be something, and is that something big or small? Small, but it has to be very hard, otherwise things wouldn't bounce off it. Inside each atom. So here is our top-down view. Most of the atom is empty space, so most of the alpha particles go straight through. There's an H in straight. But even though most of the alpha particles go straight through, there has to be something small and hard. There it is, right there, in the atoms. And the alpha particles bounce off it. So when we take those two pictures and we put them together, we're going to have most of the alpha particles go straight through, but sometimes you get the veering off, okay? A few of them veer or bounce back. Now, if we had our little nucleus, and I'm just going to draw a little picture of our nucleus here. That's supposed to be an L, not a T. Nucleus. And if we have an alpha particle, and that's a little plus sign in there, and it's coming towards this thing, what charge would the nucleus be to make the alpha particle veer off to the side? Yeah, a positive nucleus makes the alpha particle veer away from it. So Rutherford said that the nucleus is probably positively charged because the alpha particles, which are positive, were they being attracted or repelled? They were being repelled because remember, positive repels positive. And then we have our review of the plum pudding model. That's how you would label it. The nuclear atom, you can show it like this. My personal preference for the nuclear atom is to draw a circle and then have the nucleus in the center. That's the second time I've spelled nucleus with a T instead of an L. So weird. So weird. There's our nucleus. And then in here, we have electrons. And this line here, what does that line at the outside represent? It's just the, yeah, it's the outside of the atom. The outer edge of the atom. So that model is called the nuclear model. Who was the scientist? Rutherford. So now we've got three models. We got billiard ball, we got plum pudding, and we got nuclear. When you're doing your quiz, you'll want to list them in order from oldest to newest. So the oldest would be the billiard ball, then comes plum pudding, then comes the nuclear model. All right. What would happen? What would the alpha particles do if J.J. Thomson's plum pudding model was correct? Remember, the dough is very light and the electrons are really, really tiny, like little poppy seeds. Yeah, they're going to go right through. Sorry, yes. Yeah, the pudding is positive. You might expect it to be a little bit repelled, but I guess because it's so spread out, the positive charge is so spread out, it's not concentrated anywhere. So and because these particles are so fast moving and hard, like a bullet, it'll just go straight through, even though like there's something there, but it'll just go straight through anyway. Okay? Good question. So our alpha particles, whoops. And literally, Rutherford said it was as though they had taken a gun and fired it at a piece of tissue, right? That's how surprising it was. So this is like a bullet through a blueberry muffin. Crazy. Now, what would happen to our alpha particles if it was John Dalton's billiard ball model? They would bounce back. They would just be like, oh no, it doesn't like it when I try to draw lines that aren't like, it doesn't like that kind of line. It tries to make a straight line for me. Anyway, every time it hits one, it bounces back. Microsoft Word being helpful, or Microsoft Office being helpful again. And now, finally, here is Rutherford's nuclear model. What do you need to add to the atoms? You need to add a nucleus. Where should the nucleus go? In the middle. Should it be big or small? Small. And then you can show the alpha particles. This one, uh-oh, it hit a nucleus, it will bounce back. But if it doesn't hit a nucleus, it'll go straight through. Or if it hits the edge of a nucleus, it'll veer off to the side. All right. And that's it for the nuclear model of the atom. Yay! Do you know what the next model is? Oh, yes. The nuclear model is the one we were just on. What comes after the nuclear model? It's the Bohr model. Did you guys do Bohr models last year? If you did, that's great. If you did, and you may have forgotten them, which is fine. If you never did them, that's also okay. But before we carry on, would you like a small brain break?
Yes.
Yes? Brain break. So we're going to take a 5-minute brain break. We would go and walk outside, but I think it's raining today. So we will not go and walk outside. Would you like to do a stretch? No. Okay. Then would we like to just have a 5-minute brain break? Yes. Okay, back to work. We've had our 5 minutes. We're on page 32, 32. So, Rutherford just said, nucleus in the middle, it's positive. Outside the nucleus, mostly empty space with electrons sort of here and there. But Bohr said, and we're not going to go into the experiments for this. If you're interested in this, it is part of the enriched package, is going through how Bohr came up with his model. And I'll have that printed for tomorrow if anyone is interested. Okay? But he came up with this idea that in the center we had the nucleus. He got that from Rutherford, and the nucleus was positive. And then he said that there were energy levels. What's another word for energy level? Shell. Okay? So when you label these circles around the nucleus, those are called energy levels or shells. We also have the nucleus, and we also have an electron, or 3, or 7, or however many it happens to have. But Bohr said electrons can exist only on those energy levels. So you can have an electron here, where it's drawn right now, or you can have an electron here. Okay, that's okay. Or you can have an electron here. Anywhere on a shell or on an energy level is okay. Electron, 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 anywhere on a shell is fine. But what he said was that you cannot have an electron in between the shells. Nope. So the electron cannot be between shells. And the symbol that I'm going to use for electron to make it shorter to write is an E with a little negative. It cannot be between shells. Which is really weird because electrons can actually jump from one energy level to a higher one, or from a higher one to a lower one, but they don't actually pass through the distance in between, which is why small stuff is really weird. We'll talk a little bit more about that, but we won't spend a lot of time on it because it's really mind-blowing stuff that I certainly don't understand. And many of the best brains in the world didn't really understand it either. Because electrons are negative, they are attracted to what? They are attracted to positive. What in the atom is positive? The nucleus. So if you were an electron, where would you like to be? Would you like to be at location A? Would you like to be at location B? Or would you like to be at location C? If you were an electron, where would you like to be? Location A, because it's closest to the nucleus. Okay? So electrons will go in as close to the nucleus as possible. Electrons live as close to the nucleus as possible. This is page 32. But they can't get any closer than the first shell, okay? Because remember, they cannot be between shells, and they cannot live between the first shell and the nucleus. That's position A is as close as an electron can get to the nucleus. Okay, that's as close as it can get. Now, it turns out that these shells are kind of like, I like to think of this like a hotel, okay? And on the first floor of the hotel, the first floor is like the first shell. There's only one room on the first floor. And in that one room on the first floor, it's a double occupancy room. The maximum number of electrons is 2, because it's a double room, okay? So in shell number 1, the maximum number of electrons is 2. So the shell is kind of like the floor of a hotel. And shell number 1 has 1 room. Shell number 2 shell 2 has, can anyone guess how many rooms it has based on the maximum number of electrons? Each room is a double occupancy. It has 4 rooms. Yeah. Yeah. Shell 1 has only 1 room. Yeah, it's 4 rooms, each of which can hold 2 electrons each. So that's the maximum number of electrons you can fit on that shell. You don't have to have the maximum. You can have fewer than the maximum, but that's the max. Shell number 3 has a maximum of 8 electrons. How many rooms does it have? It has 4 rooms as well. And then shell number 4 is weird. Technically, you'll hear that it can hold 18 electrons. But the Bohr model actually breaks down at element number 20. So we don't end up drawing Bohr models for anything past calcium. So we'll only ever put 2 electrons into the 4th shell, and then we'll stop drawing Bohr models after that. Okay? But technically, it has 18. How many rooms would that be? Has 9 rooms. Okay, but we're just going to get rid of that because it doesn't really matter. So here is lithium. Do you remember seeing a periodic table with, it's got the symbol for lithium, it's got the name. We got our symbol. We got our name. Then at the top is what we call the atomic number. Anyone remember what the atomic number tells you? Yes. Amount of protons it has. So the atomic number, this is the number of protons. And the symbol we're going to use for protons, can you guess? Yeah, P with a plus, absolutely. Okay, so the atomic number is the number of protons. But if you remember, if we have 3 protons, how many electrons would we need to balance out that charge to give us 0? Remember, the atom is neutral. Same amount, yes. So we're going to have 1, 2, 3 electrons. Now, that's a really ugly drawing, yes? Because I've made my nucleus really big, and I got my electrons just sitting around randomly. So let's organize them as we should on a Bohr model. If we have 3 electrons, so the atomic number tells you the number of protons, but it also tells you the number of electrons. And tomorrow I'm going to give you your own periodic table so you can look this stuff up, okay? Remember, we have 1 room. This is shell 1. Double occupancy. So 2 electrons are going to go in that first room because it's as close to the nucleus as possible. That's where electrons like to live. And then the 3rd electron is going to go into one of the 4 rooms. Shell 2 has 4 rooms. And so we're just going to put the electron in any one of those rooms. It doesn't care which one. Usually I put it at the top just so I don't get confused, but it doesn't matter really. Okay? And I think we're going to leave it there for today. Your homework is going to be page 19, 20, 21. Page 20 is all enriched, so it's optional. Okay? Page 21 is practice for your quiz. Okay? Oh, yeah, no, this is my Chem 12. Chem 12. Yeah, I'll try it out. Actually, yeah. You know what? Okay. Oh, if there's anyone who's staying today for correction.